All right, they usually do.
Without loving action, we miss the meaning of life.
Hey, how you doing? Good. So yeah, you have her bio, right?
Yep, okay.
Okay.
He's looking it over.
Good, good, good.
Can I use this pen real quick to sign?
Huh?
Can I use this pen real quick to sign?
Oh yeah, yeah. So, what's the status right now of the,
I gotta talk to Mrs. Johnston. I emailed,
okay.
but obviously I'm gonna have to.
Yeah, we need to
I'm gonna
get
talk to her. It says
April
It's gonna
dates.
have, you guys gonna have to get it. So,
Yeah.
there is some possibility that that's our only available date. And in that case, we
Oh,
probably have to move on to a different speaker potentially.
actually, yeah, that's a conflict for me too. Because on that date, we actually have, we have these joint bio camp. Yeah, we have one scheduled for that date,
For the first?
for the first.
Okay, I'll look into see what else there is.
Yeah,
All right, sounds good.
okay,
Thank you.
no problem.
care, we cannot survive. Without loving action, we miss the meaning of life.
Hello.
Hello.
Hi, how are you?
I'm good. How are you?
I'm doing good. So let's try to get you, make you a co-host too. And you should be able to share your PowerPoint.
Yeah. 1 second.
What time is it out there?
It's 1:27.
Oh, okay. All right.
Okay, can you see my screen?
We can see your screen. So you want to do full screen though?
Yeah.
There you go. Do you
Okay.
have video or something like that?
No.
No? Okay,
No.
that'll make things easier.
Okay.
Mm-hmm. So yeah, so it's one something, and I'm assuming you guys are having much better weather than us too.
It's very nice here.
It's very nice. Let
Like
me
80 degrees outside.
80 degrees. Oh my goodness. Let's
Yep.
see what we have here today. 40.
Yeah.
And in Trinidad and Tobago, where I'm from, originally, it's 81. So it's
Oh,
like,
nice.
yeah. We will have one of our undergrad students introduce you. You want to come say hi to Kristen, Dr. Gardner?
Hello,
Hello. How are you?
my name's Suvan Campbell. I'm one of the seniors here
Nice to meet you.
introducing today.
Yeah, so you are biochemistry?
Yeah, I'm a biochem
Biochem.
pre-med.
Oh, nice.
Yeah. Good. So we um, could get the perspective of a postdoc today.
Yes.
Yeah, we've had a pretty varied series, but you've been the first postdoc in a long time.
Oh, well, thank you for the invitation.
Yeah, been a while that we've had. So go ahead and hit. If somebody wanted to be in the middle, Ryan, yeah, yeah. And once we get started, I need to hit, there's record down below there, someone on the, oh, yeah,
It's going already, I think.
is it?
Yeah, it's recording.
I forgot to pause it. That's okay. That's all right. We didn't say anything incriminating. Uh, So if you want, you can get started. But it's.
Give it a second and then
Yeah.
maybe like 1 more minute.
Okay. Right there too. I don't know what you.
All right, let's get started then. So our speaker today is Kristen Gardner. She is currently doing her postdoc at Caltech, where she's studying nickel catalyzed cross electrophile coupling. She graduated with a BS in chemistry with honors and distinction in 2019 at UNC Chapel Hill, and she got her PhD at UC Berkeley, where she studied the diversification of 2-pyrone into a variety of different ring scaffolds for both novel methodology development and the total synthesis of cephalotane type diterpenoids. She is dedicated to teaching new scientists and hopes to, in the future, teach at an undergraduate level to help create a more inclusive environment and help underrepresented scientists find their place and their voice. So let's welcome Kristen Gardner.
Thank you for that introduction. I'm really excited to be here today to talk to you a little bit about my work. The last chapter of my PhD at Berkeley, where, as it was mentioned in my introduction, I was really focused on this molecule right here, which is known as 2-pyrone. And in this particular study, I'm going to walk you through how we discovered this rearrangement where at very mild, under mild reaction conditions, we're able to access what are called aryl amines, where you have this aromatic ring with a nitrogen substituent. And so to start, I want to talk a little bit about what my motivations are for organic synthesis. And in particular, through about both my PhD and postdoc, I have thought about both the total synthesis of natural products. And so that is often where you're taking something that's been isolated from nature, whether that be from a plant or a marine sponge, and it might have some biological activity. And so we go in the lab and we try to make it so that we can study, so that biochemists can study it on larger scale. And so I spent a lot of time working on that. But I also work on method developments like this project that I'll be talking about today, where we're trying to develop a new methodology that helps enable other synthetic chemists in their chemistry. In particular, I think that these two are really connected, where the need to synthesize some new natural product, there might be some gap in the field, which leads us synthetic chemists to develop new methods. And on the other hand, once a method is developed, it may be applied towards the total synthesis of some natural product. And so when we're picking a target or something that we are interested in studying, we often think about function, strategy, as well as the structure of what we're trying to synthesize. But today I'm just going to focus on function and strategy. And so when we think about function, you can think about biological activity, for example. And so delave 18A is this natural product that has been isolated from Chinese plants, and it has some anti-cancer and anti-inflammatory properties. And so because of these properties, it is of interest in the pharmaceutical industry to have some potential utility. And so in the Sarpong group's decision in this molecule, right, the function of it is the fact that it has these anti-cancer and anti-inflammatory properties. On the other hand, we might pick a target based on strategy. There's a lot of different things that you can think about, like maybe you want to follow the biosynthesis, but in this case, our group had a symmetry-inspired approach. And so what I mean by that is if you look at this 2-pyrone scaffold here, it has these substituents highlighted in red that are symmetrical, and they map onto delave 18A as shown on the left. And so this strategy to design the symmetry-inspired approach led to the discovery of this cascade process where this 2-pyrone was remodeled into del-18A. And I did not work on this project, but this total synthesis really inspired my entire PhD and inspired the desire to develop new methodology with these 2-pyrones. And so I want to introduce 2-pyrone a little bit more. And so pyrone is a really versatile building block. It's been used many times over the years for the synthesis of complex molecules. And there's usually 2 different ways that we think about making these molecules. The first, or transforming these molecules. The first is through direct pericyclic processes. And so, for example, if you take this 2-pyrone and you shine light on it, it can undergo a disrotatory 4-pi electrocyclization to yield this bicyclic lactone intermediate. This bicycle can then be further elaborated and transformed. Alternatively, you can take 2-pyrone, which contains this diene, and it can undergo a 4+2 Diels-Alder cycle addition with an alkene or an alkyne to yield these 2,2,2 bicycles. Both of these ring systems have been further transformed, and they both have actually been applied to the total synthesis of natural products. For example, in 2019, the Nelson group was able to synthesize vibrolactone using this photochemistry pathway. And alternatively, the Diels-Alder 4+2 cycle addition chemistry was used by the Snyder group in 2013 towards the total synthesis of sclerosine A, as well as our group's work towards natural products such as sapphirolide F. And I did actually have the opportunity to work on this project, although I won't be talking about it today. But this first kind of category where you take 2-pyrone and react it in some sort of pericyclic reaction to form a new bicycle has been widely applied in total synthesis. On the other hand, the Sarpong group was really interested in what we call annulations that are enabled by ring opening of 2-pyrone. And so what I mean by that is that this is our 2-pyrone scaffold. And depending on the nature of the nucleophile, the pyrone can either be opened in a 1,2 fashion to this ring-opened intermediate, or the nucleophile, depending on nature, could attack at the 6th position to get to this ring-opened intermediate. And we are really interested in how you can engage these ring-opened intermediates in further cyclization chemistry to form new rings. This was really the cascade kind of pathway that allowed our group to access del-18A from 3,5-dibromo 2-pyrone, where this is a retrosynthetic arrow. So that just means it's we're able to make this product from this starting material. I'm going to break this paradigm down step by step. But the first thing I want to do is introduce cross-coupling reactions in case you're not familiar with them. And so a cross-coupling reaction is a really powerful transformation that in 2010, there was a Nobel Prize awarded to Heck, Negishi, and Suzuki for their palladium-catalyzed cross-coupling reactions. And so in this case, we're bringing together 2 fragments with the help of a metal catalyst. One of those fragments is considered your electrophile. In this case, the R group highlighted in blue is bound to some sort of halogen, such as bromide or iodide or a triflate. This reacts with your nucleophile, which is bound to some sort of metal, such as boron or tin. And with the aid of palladium catalysts, you're able to bring these 2 fragments together to form a new carbon-carbon bond. Mechanistically, you start from this palladium precatalyst, which ends up on cycle as a palladium 0 species. From here, this can undergo oxidative addition into your electrophile. And so what that means is that the palladium inserts in between the RX bond to form this palladium 2 intermediate, where palladium is bound to the R group and it's bound to the X group. From here, this intermediate can undergo transmetallation, where palladium is a metal, and you have some sort of metal bound to your nucleophilic R group in red. And so the R group goes on to palladium, and the X group goes on to your second metal in that transmetallation. And then you end up at this palladium 2 species, where now a reductive elimination, which removes the palladium, allows you to form your RR bond. An example of this in total synthesis is that they were able to take this quinoline, where I've highlighted the, electrophile in blue, where the pseudo halide is this triflate. This can react with what's formed in situ as this copper acetylide, so our nucleophilic species, through what's called a Sonogashira cross-coupling reaction to form this carbon-carbon bond. And what they found in this chemistry is that when they treated with acid, they were able to directly form the natural product, cassiarin. I wanted to talk about this because all of the chemistry we do with pyrone usually starts with some sort of cross-coupling reaction. And so I think it's good to orient you to some of the actual chemistry that we're doing to make these starting materials. And so now I want to return to kind of this paradigm to explain how we imagined we could form a variety of different ring systems from this common starting material. And so this is known as 3,5-dibromo-2-pyrone, where you have a bromine at both the 3 and the 5 position of this 2-pyrone scaffold. And the first step in our remodeling is this site-selective cross-coupling. And so, for example, if we want to specifically cross-couple to the C5 position of pyrone, we discovered that we can do so with polar solvents in the presence of copper iodide to, for example, install a phenyl group where this bromine was, as shown here. Alternatively, if we want to first do our cross-coupling at the C3 position, we can do so in pretty much any other condition to get our phenyl group at C3. Being able to control where each R group goes allows us to perform sequential cross-coupling reactions where, in theory, we could put whatever group we want at the C3 and C5 position of the 2-pyrone. From here, we're interested in this regioselective ring opening, where we first imagined exploring opening pyrone in a 1,6 fashion. We know that if we subject pyrone to sodium cyanide, cyanide attacks at the C6, and the resulting carboxylate can be trapped with methyl iodide to give access to this acyclic diene shown here. And from here, we were interested in exploring new cyclization events, where we imagine EZ isomerization around this double bond to set up our R1 group to engage with this diene in some way to form a new ring. And so the idea really was that by changing what we put initially at C3, we could potentially access a wide variety of different ring systems, with this R2 group being a second area for diversification. But we were also interested in revisiting the regioselective ring opening and wondered if we could instead affect a 1,2 ring opening using a harder nucleophile such as sodium methoxide, where methoxide would attack at the carbonyl to get to this ring opened intermediate. And from here, we'd explore similar cyclization events where you can imagine EZ isomerization across this double bond, as well as tautomerization of this enol to the aldehyde to set up our R1 group prime to engage with our aldehyde in some way to form a new ring. And so really the entire platform for this remodeling, what I spent most of my PhD working on, is that we can take advantage of cross-coupling to put what groups we want here. And then depending on the nature of the nucleophile, we could follow one of these 2 pathways to access a variety of different ring systems. And I don't have time to go into all the details today, but this works. So this was the strategy that was employed for the total synthesis of Del 18A. But also during my PhD, we were able to access these nitrogen-fused heterocycles. This is called a Pareto 1,2A indole, where the parts that come from pyrone are highlighted in blue, and the nucleophiles in green. And lastly, I was able to access these substituted benzoates from 2 pyrones, and I do briefly want to talk about this as it ties into the aryl amine chemistry. And so starting from now, this 2 pyrone containing a triflate at the 3 position, we could perform a Sonogashira cross-coupling with phenylacetylene to get to this 3-phenylalkynyl 2 pyrone. When subjected to sodium cyanide, the cyanide attacks pyrone in a 1,6 fashion, and the resulting carboxylate could be trapped with methyl iodide to give access to this intermediate here, which is known as a diene, because it contains both a diene as well as an alkyne. And from here, I was really interested in something called the Hoff cyclization. And so under thermal conditions, you could envision this double bond undergoing easy isomerization to set up our diene to engage directly with our alkyne. And then at very high temperatures, this could undergo a 6-pi electrocyclization to form this allene intermediate, which could undergo a formal 1,5 hydrogen shift to yield our desired aromatic product. I want to note that this sort of 6-pi electrocyclization with a linear alkyne is typically forbidden at low temperatures, but there are reports in the literature that if you heat these things to like 500, 800 degrees Celsius, you could enact this sorts of transformation. Additionally, there's been a lot of work recently to do this with the aid of a metal catalyst in order to allow this reaction to occur at much lower temperatures. And so I was interested in taking our dienes to these aromatic products with the aid of some sort of catalyst. And so what I found was that these dienes, when treated with 20 mole% of this rhodium dimer at elevated temperature, I was able to access the desired product. And when this R group capping the alkyne was a phenyl group, I was able to isolate the desired product in 70% yield. However, the reaction requires a very high loading of rhodium. So if you think about 20 mole% of a rhodium dimer means you have 40 mole% of rhodium in solution. So you have a lot. So you're not getting very good turnover of your rhodium substrate. And in addition, the substrate scope was pretty limited. So this R1 group had to be aromatic. If I made it something that wasn't aromatic, such as like an alkyl chain, the reaction didn't work. And if I wanted to put a substituent at this position where the R2 group would be, the reaction completely shut off. And so for me, as someone who spent a lot of time trying to affect this cyclization, it was pretty disappointing that it didn't work very well. And so what I wanted to do was kind of see if there was a way to redeem the reaction. And so mechanistically, what I think is going on is that rhodium coordinates to your alkyne, which is your electrophile, to make it more electrophilic. So to make it easier, or to make it want the nucleophilic attack more. And then we have this terminal alkene, which I thought was acting as our nucleophile. But I want to note that this terminal alkene contains this cyano group, which is electron withdrawing. So that means it's pulling electron density away from the double bond, making it less nucleophilic. And so I wondered if the fact that this was a cyanide was the problem, and that maybe if I revisited the initial ring opening and chose a different nucleophile, if I could increase the reactivity in this transformation. And so I turned to secondary amines. And so secondary amines we had previously reported could open pyrone in a 1,6 fashion. In our prior exploration of this chemistry, we always found spontaneous decarboxylation. And so what you could propose is that upon 1,6 addition and decarboxylation, you would get to this sort of diene. And in fact, I was never able to keep the ester intact. And so this is really not a direct comparison. So normally, if you want to make one change in a reaction, right, you want everything else to stay the same. But in this case, the ester is disappearing and our nucleophile is changing. But what we found is that when you subject to morpholine, the secondary amine, we actually were able to see a cyclized product right away. What you would expect is that if the morpholine attacks at the 6th position and undergoes similar cyclization to this rhodium chemistry up top, you would get this product here, where the nitrogen is next to the 2 phenyl groups, or ortho. However, instead, I isolated this product where the morpholine was para to this phenyl group. I isolated this in 74% yield at room temperature, and this was confirmed with an X-ray crystal. This was a really interesting result because it was not what I was expecting at all, right? The morpholine seemingly shifted. If it's opening at carbon 6, it's not ending up at carbon 6. And it was pretty exciting because the reaction did not require the addition of a metal to affect the cyclization. And we could tolerate substituents at both the C5 position and the C3 position of pyrone. And so although it was like this unusual rearrangement that I found very fascinating to study, it was exciting because it kind of redeemed the yield and reactivity of these species. And so what I want to do is kind of walk you through the proposed mechanism step by step, just so you can kind of understand what we think or what we propose is going on from how this pyrone is actually getting to this aromatic product. And so starting from this 2-pyrone, we believe that morpholine adds in a 1,6 fashion where you can push electrons up all the way to this carbonyl. And after a proton transfer, you get to this neutral intermediate here. From here, this can undergo a tautomerization, kicking down electrons from this alcohol onto the alkyne to form this alene intermediate. Now, this alene is in conjugation with this carbonyl, and what we believe is that then a second equivalent of morpholine adds in a 1,4 fashion to get to this product here. And so we believe there's actually 2 equivalents of morpholine involved in the reaction. And from here, this can undergo an electrocyclic ring opening to yield this triene. So it has 3 double bonds in a row, still with the carboxylic acid intact. And that this can undergo easy isomerization across this double bond to set us up for the cyclization event. From here, we believe that this can undergo a 6-pi electrocyclization to get to this cyclic diene intermediate. Proton transfer, kicking electrons down from this nitrogen, yields this zwitterionic intermediate, which can now undergo a decarboxylation to this intermediate, followed by elimination of 1 equivalent of morpholine would yield our aromatic product. And so this is our proposed mechanism. And for the sake of simplicity, I'm just showing the arrows and what we think is going on. But I did have the opportunity to work with Louis Delesquier, who was a graduate student in the Peyton Lab at Colorado State University at the time, and we were able to model this reaction. And so you don't really need to get bogged down on this, but essentially we modeled every step using computations, and we believe that this is a very feasible reaction where the highest barrier is this key 6-pi electrocyclization. And so now that I've proposed a mechanism, I'm going to talk to you guys a little bit about the scope of the reaction, where it was optimized, where both R1 and R2 were phenyl. For the scope, I had the pleasure of working with Jin Tan. She was a very talented undergraduate at UC Berkeley, who I spent time working with, and she's now a graduate student at UC Irvine doing her PhD in chemistry. And so we first looked at changing the R1 group. So we looked at changing the group on the alkyne, and we found that we could tolerate a wide variety of groups, including electron withdrawing and electron donating groups. And although low yielding, when this R1 group is not aromatic, we do still see yield at room temperature. Then we looked at varying the R2 group and found that although in general, increasing, we saw some decrease in yield. We could tolerate electron withdrawing, electron donating. We could have a different heterocycle. And the real limitations came when we tried to put something that was not aromatic at R2. And so having kind of explored the pyrone scope, we wanted to take a little bit of a look at this scope of amines that were tolerated in this reaction. And so in this case, we kept both phenyl group on the alkyne and at the C5 position, and we varied the types of amines we subjected. I've classified these amines, and so the first set I want to look at is the cyclic amines. In general, cyclic amines are well tolerated in this reaction. We can put other heteroatoms in the ring. We can have a free alcohol. We can have an electron withdrawing group. And in general, we see pretty good yields, except for when we start to increase steric bulk around the nitrogen atom. So when you put this methyl group on the carbon next to the nitrogen, we see a decrease in yield. But once you move it further away, so it's further from the nitrogen, the yield goes back up. And so in general, cyclic amines are well tolerated. We then looked at acyclic amines. So we looked at amines that weren't contained within a ring, And in general, they worked, but they did not work as well as cyclic amines. If you're thinking about the difference, right, it seems like cyclic amines, which are kind of locked in a specific conformation, they're stuck in a ring, tend to work better than acyclic compounds that have more freedom of rotation. And for completeness, I do want to show you amines that did not work in this reaction where I just recovered starting material. And as you can see, a lot of them have steric bulk around the nitrogen atom, although we did have some interesting results like this bismethoxyethylamine where I saw no reactivity at all. And so this was interesting because we could tolerate these different amines. And I personally, like as an organic chemist, just like looking overall, thought I started to see trends in which steric bulk seemed to be a problem, as well as having like a less locked conformation. And so I actually wanted to see like, hey, if you were to come to me and say, Kristen, can this amine work in the reaction? I wanted to see like, could we build a model that would predict whether or not the amine would work without actually having to run the reaction? And so to do that, I collaborated with the Sigmund Lab, which is a lab at the University of Utah. And I worked with a very talented postdoc at the time, Dr. Melissa Hardy, who's actually one of my dear friends because she did her PhD also in the Sarpong group, and we used to work right next to each other. So it was really cool to get this opportunity to work with her once she had left the Sarpong group. And so I'm going to walk you through the workflow for how we built our model to predict whether or not an amine would work. I'm going to do this at a very high level because I am not a computational chemist. And so the first thing that we did was we identified possible secondary amines. And so for us, that meant amines that were available to us in the lab. So what I did was, like the Sarpong group is a very big lab. We probably had thousands of chemicals. I went through our inventory and found every single possible secondary amine, and I sent that list to Melissa. That way, whenever she needed me to run test reactions, I could literally like go in the lab that day and run the reaction because I had the starting material, the secondary amine available to me. I wasn't going to have to make it or order it. And so we limited ourselves to stuff that was available in the Sarpong group. With those substrates in hand, we performed a macro model conformational search. And so basically, we took every single possible secondary amine, and Melissa performed a conformational search where it found every single possible conformer, so every single possible way that that amine could sit. And we did this within a 5 kcal per mole cutoff. With all of the possible conformers, we then did a Gaussian geometry optimization. And so what that does is for every single secondary amine, it took every single conformer and it tried to minimize that starting geometry. So it was to find the most stable geometry of that conformer. This is done at a pretty high level of theory, which means it's less expensive in terms of like time-wise and using computational resources. And then once the geometry had optimized, there was a single point optimization done, which is done at a higher level of theory. It's not to like do anything with the geometry, but what it helps find out is other properties about that conformation. And so those properties are typically electronic. So you could think about NMR chemical shifts. It could be the non-bonding orbital energy, dipoles, things like that. From here, we did an atom number collection. And so how I understand this is that an amine, right, the secondary amine could be X number of atoms. It could be, right, we have the cyclic ones, the acyclic ones. But what we care about is what's close to the nitrogen center because the nitrogen is acting as our nucleophile. And so in order to kind of centralize those properties around the nitrogen atom, you number the nitrogen and you number any atom directly connected to it. And that just kind of takes the properties that we've extracted and centralize them to that part of the amine. From here, Melissa was able to get the properties for each conformer. And with those properties in hand, we could now use descriptors to model. And so this workflow spit out certain descriptors. It could be electronic descriptors, or it could be steric descriptors, such as steric bulk, electronics, how much electronic, whether there was a lot of electron density at the nitrogen or not a lot, things like that, or a mixture of both. And so I'm going to show you our final model, but realistically, that's not what actually happened. And so, right, it took us a little while to settle on this model. But we found a model that's just one parameter and it's a steric parameter. So this here is one of our secondary amines where this nitrogen atom is shown in purple. And this parameter, what it does is you take a 3 angstrom radius and you draw a circle around the nitrogen atom. And what this parameter looks at is how much steric bulk from that like what else is on the nitrogen falls in that circle. From here, we are able to build a model where yield is directly related to this parameter. This parameter is called the percent buried volume at nitrogen within 3 angstroms. And in this case, we did it of the lowest energy conformer for each secondary amine. And so we were able to build a model. I'm going to walk you through this because there's a lot going on. And so on the x-axis is the yield measured. And so that's the yield that I measured in the lab. So like when I went and ran these experiments, those are the yields that I got. The y-axis is the yield that was predicted by the model. So for example, for this amine shown in just this black dot, right? The yield that I measured in the lab was, let's say, like 23%, and the model predicted it would be like 10%. So that's kind of what you're looking at. The black dots are the training sets. So those are the secondary amines that we use to build the model. Like I gave Melissa some results and she used it to build a model. From there, you can get an R² value. And so that's a linear fit of all of your different results. You normally want this value to be as close to 1 as possible. We were pretty happy with 0.78 because yield is particularly hard to model for reasons that people can ask me about if they want, but because of how hard it is to model yield, we were happy with that. Then you can figure out the Q². And so what the Q² is so basically we've built the model. We have the fitted line using the black dots, which are our secondary amines I ran in the lab. Now what we're going to do is we're going to take this amine, for example, and we're going to remove it from the training set. So originally it was in the training set to help us build the model, but now we're going to say, let's take it out of the training set and then ask the model, what does it predict the yield is going to be? And so that's called leave one out, where you one at a time remove amines and ask it to recalculate it. And so the black dot, like I said, is the training set, and the white is what happens when you leave it out, so what it predicts. So for some of them, you do see some difference. For example, for this amine, originally, when it was part of the model, the yield was predicted to be, maybe 10%. And when it was removed from the model, it was even lower. But some of them have pretty good overlap where you can't even see that leave one out white circle. And so from there, you can get a Q², which once again is just a linear fit, but now of those white dots, which is in pretty good agreement with our R² as we want. And then this MAE is the mean average error. So it's the average error between the predicted yield and the yield I actually measured in the lab, which 10%, not amazing, but we were okay. We were happy with that. So then you got to make sure the model actually works. And so what we did was Melissa said, run these 4 amines. And so these are the red amines. And so basically the model predicted a yield. I went in the lab and I ran it. And so, for example, this amine here, where I saw no reaction, is this red dot here, where the yield I observed in the lab was 0% and the yield it predicted was 0%. I mean, it may look a little negative, but you can't have negative yields. And so this kind of validated that our model worked. And although it's not perfect, so our R² for our test set was pretty similar to our training set. And the average error between the predicted and measured yield went up to about 15% error, or like 15% difference in yield predicted versus yield measured. And so it's not perfect. You might not get the yield exactly right, but it is a pretty good model that kind of can tell you whether or not an amine works based on steric bulk. And so it suggests that if there's large R groups within this circle, you're going to get a lower yield, which is kind of what I got from just looking at the scope. And so that kind of wrapped up this work. And so in summary, we were able to kind of discover this unusual transformation where under very mild conditions, this 2-pyrone could be rearranged to aryl amines This work was published last year in Chemical Science, and it kind of overall expanded the toolbox for core modifications we can make from 2-pyrone. And so we can access all of these different ring systems where, once again, the actual like part that comes from pyrone is shown in blue, all from this common intermediate or a common starting material. And with that, I just want to thank my PhD advisor, Professor Richmond Sarpong. This is him right here. It was absolutely amazing to get to do my PhD in this group. He provided a lot of support and mentorship as I kind of explored a lot of different projects. Jin, Louie, and Melissa, these bolded people were collaborators directly on this project that I mentioned them as they came up. And I had a lot of my other projects going on in the group that I worked on with these previous members, in particular, Juliet and Aaron, who were both undergrads at the time that I was working with them. The rest of the Starpong group, which was just a great environment for me to do my PhD. The Center for Computer Assisted Synthesis. So I had the privilege of working with people from Colorado State University, University of Utah, and that was all facilitated through this kind of NSF center. And with that, I'll take any questions you guys may have.
Right. Thank you so much for the talk. So I'm gonna start off the questions. I'd first like to ask, so it appeared that most of those reactions were about 16 hours.
Yes.
How much time total would you say you spent just running reactions? And it didn't seem like the reactions required a lot of observation, but I mean, it's still like time.
Yeah. So I guess to answer that, these are really easy reactions to set up. You literally just like take your starting material, you dissolve it in THF, and then you add your amine, which is usually a liquid. And I literally would just cap them and I could just leave the reaction until the next day. So they were extremely easy to set up and work up. Like I could be done setting them up in half an hour. Workup might take another half an hour. But overall, these are really easy reactions to run, which is nice. And 16 hours, I kind of did that purposely, right? Like that's like the perfect amount of time to be able to set up a reaction on like a right before you go home from work and then work it up the next morning.
Mhm.
Yeah.
Anyone else have questions?
I have I have several questions, but I'll begin with, did you or has anyone started looking at primary amines instead of secondary?
That's a great question. So I did try primary amines. So it is known that if you subject pyrone to a primary amine, that you can form pyridone. So that would be if you'd have the nitrogen here instead of oxygen. So it would add in either. The literature is kind of mixed. It doesn't know if primary amines actually add in 1,2 or 1,6, but basically you end up rearranging it so that you lose your oxygen and end up with a nitrogen there. I observed something similar, and so that is a limitation of this work.
So the follow-up question is then, so I'm sure you're pretty familiar with the wine rep, amide.
Yeah.
So that would be a secondary amine, but now, so it has a methyl group attached to
Yep.
nitrogen and a methoxy group also attached to nitrogen. So that's secondary, but it involves like a supernucleophilic nitrogen.
Yep.
Did you or anyone, look at that particular type?
Yeah, that's a great question. I didn't end up looking at it. Those would have been interesting to try for sure, but we didn't explore them.
Okay.
There any other questions that we have?
I could follow up with some more. So you were doing postdoc. What's the name of your postdoc advisor again?
Aryl Reisman?
Yes. I actually tried to get her also to do a presentation, but anyway, what is your postdoc research involving again?
Yeah, so It's actually, I work on catalysis, both nickel and samarium. So I'm looking at development of new reactions where either samarium or nickel is the catalyst.
Okay, and for what type of reactions? Are these cross-coupling?
Great question. So for nickel, it is cross couplings. Nickel, we're looking at cross couplings between alkyl chlorides and aryl chlorides. And we want to do that in selectively. And then for samarium, I am actually looking at hydrogenate. Basically, we've developed a system. So samarium is super powerful. So samarium, if you don't know, like really likes to react with carbon oxygen double bonds, but then it forms a really strong bond with oxygen. And so it's hard to do that chemistry catalytic. We've discovered a system in order to get samarium to turn over so we can develop catalytic systems. And so we're looking at hydrogenation reactions catalytically with samarium.
So
So like
samarium,
1,4 reductions.
so from what you observe in there, samarium is an oxophilic like Lewis acid. It kind of goes to oxygen.
Yes, but I joined the project after the catalytic system had been discovered, but someone discovered that if you tune it with the right amount of acid, you can actually turn over the catalytic system and get break the samarium oxygen bond.
Oh, okay.
Yeah. It came out in Science last year, so we're kind of following up on that work.
Oh, okay. And that's from the current lab that you're in.
Yes.
So you also mentioned your future,
Mhm.
and stuff. And I think you mentioned going to teach at an undergraduate institution.
Yeah.
What sort of like motivation and factors in that sort of decision?
Yeah. So um my favorite part of graduate school was actually like getting to work with other students, getting to mentor students. I worked with several undergraduates. I worked with uh younger graduate students like who are younger than me, right? And so what I really enjoyed was getting to teach them and help them and see them succeed in their chemistry. And I think that research is a really great platform for teaching. And so I would like to work at a primarily undergrad institution. I want to have my own research lab, but I really want it to be focused on teaching the next generation of scientists. So whether both in the classroom and in the laboratory.
Very good. That's a good choice.
I've got a question online.
Hi.
I enjoy your talk. I was working in my office here. Yeah, I got to do some cross couplings in graduate school. It's great to see you expanding a lot of that work and showing the utility. But you were talking about modeling, I'm assuming some mathematical modeling. I'd wondered if there was any like artificial intelligence that you're trying to employ that maybe then could take this information and start, applying it in different areas.
Yeah. So Um, I don't think anyone was working on AI in general, in the context of anything that I was working on. And my postdoc lab does machine learning as well, but we're not doing anything AI related really right now. A little bit of like predictive, like you can give it a target and say, how would you make this molecule? And you can compare that to like what a synthetic chemist would come up with. Um,
Nice.
And I think the synthetic chemist, like it's a good starting point, but I think there's still a lot of flaws in what the computer actually like the computer's not going to replace us yet, in that
Right.
regard.
Yeah.
But I think in terms of uh, we weren't really using AI, but like the Sigmund group was also just like building a model of trying to like model all secondary amines just so there was a database so that anyone could kind of pull that information. And so I know a lot of groups are doing things like that, but not AI.
I feel like
Yeah.
that's sort of the next step, right? I mean, you
Yes.
got such a great data set that you start can train these systems to, take it to the next level. So yeah, maybe some more opportunities there to work with a computer department or some other faculty there. And
Yeah.
great
Great.
work. That's fun.
Thank you. Thank you.
Yeah.
Yeah, just as a follow-up to that, during one of the summer research experiences I've had in the past, one of the professors that I worked with brought up a program called like Minitab, I think, which was looking into how you can I believe it was predict like how a reaction would go. So similar to the work that you did. And it was talking about just essentially optimizing reactions. And you essentially put in a set of parameters, and through that you're able to design your experiment as it helps you choose which would be best. I don't know exactly the details into that. I just know that she had brought it up as like a potential use. And so I was wondering if maybe you had heard about that or if something similar.
Yeah. I haven't heard of Minitab, but like a lot of what we do, right, is like uh, in my case, we were simply just like, can we get like a yes or no kind of print, right? Like if this amine will work, this amine won't work, and prediction of yield. But a lot of reaction development will be right where you try a standard set of you like try conditions. Like let's say you're trying to optimize A to B and it has five like different reagents over the arrow. And so you try a bunch of conditions and then you tell the computer, hey, what do you think I should try next? So there is a lot of modeling, especially with like cross-coupling reactions to do that sort of chemistry. I just want to be honest, I'm not a computational person. That's more of like I let them do that. I just give them the organic chemistry data.
Wondering.
I've got one more quick question, I hope,
Okay,
Yeah, go
if you
ahead.
don't mind.
yeah, go ahead.
Maybe I missed it. How did you measure your yield? What analytical techniques did you use for the yield?
Yeah, so I ran these reaction or I like actually isolated the product. So I ran the reaction, worked it up, and then I used column chromatography to isolate the product and then proton carbon high res mass spec to get the confirm.
Any mass spec or?
So at it's funny because I only basically used mass spec like at the end of my right just to like get that data point for the paper, right? To like, but here at Caltech, we have like a whole catalysis center. So there's a lot more, right? Like people will run reactions and monitor it using like an LCMS or a GCMS or like get a lot more data throughout the process using those
Yeah.
analytical techniques, which I didn't really have the opportunity to do surprisingly well at Berkeley. We mostly used NMR.
Oh, okay. Yeah. I mean, I feel like if you nailed the NMR, right, and it matched up, it was pretty definitive. We
Yeah.
always did. I built some bigger molecules and we did MALDI-TOF and it was kind of nice to have both.
Yep,
And
for
so
sure.
anyway, all right, cool. Yeah. Column chromatography, go through a lot of silica gel and
Yep.
yeah, yeah. Did you use
Yeah.
pressure? Did you pressurize it to try to speed it up or get some better?
Yes, we did flash
Yeah,
column chromatography. So
good.
sure. Yeah.
Good job. Yeah, that's great.
Yep. Thank you.
Thank you.
So yeah, another question, how accessible and affordable are the two pyrones?
That's a great question. So it depends. Okay, so like 3,5 dibromochupyrone is one step from commercial. So you can make it from kumalic acid, which would be so kumalic acid is where you have an ester here and no substitute at this group. So that's pretty commercial and easy to access and not super expensive. But the bromination uses so much NBS. So that wasn't great. If you wanted to instead make the triflate, so where the other substrate that I used where you don't have a substituent here, actually you just have the triflate coming off the 3 position, that was from mucic acid, and that was like mucic acid is like dirt cheap and it's very easy to make a large amount of that, but you do a pyrolysis. So you like take all the reagents and you like mix them up and then you literally just take a Bunsen burner to it and heat the whole reaction mixture and then you collect your products on the other side. Like it my brain is blanking. I'm sorry on the word. Sublimes. Thank you. Sorry, it sublimes and then you like collect it on the other side. And so that I think is more accessible and you can make a lot of it. That's what we use for like our total syntheses for those compounds, the triflate. But you can get access to it. It's just not, if you want to have a cross coupling partner, you're going to need to do an extra step.
But so instead of an alkyne,
Yeah.
if you had, I don't know if you did it or not, but if you had a vinyl group, double bond instead of a triple bond, did you guys
Yep.
look into that to see what sort of like rearrangement might take place?
Yeah, that's a great question. So I did not, I thought about it. I don't have any, I don't know why I didn't put any backup slides, but sorry. But essentially, like, um, I looked at putting sorry. I looked at putting a cyclopropyl group at this R1 position. So we were actually interested in kind of breaking the cyclopropyl ring open to get the 7-membered rings. So we looked
Yeah.
at that, but that was like a summer project for my undergraduates. And then the other thing is we mostly put other heterocycles there. So like the Peridot 1,2-A indole project, right? You would cross couple an indole, and that would cyclize. And we did cross couple an indole to C3 and then open it in a 1,6 fashion and do like an electrocyclization. So you can do the 6-pi electrocyclization to get to a carbazole instead of the Peridot 1,2-A indole. If that makes sense. So we did try some other groups for sure.
I think, yeah, there's potential for other interesting chemistry by playing around with some other groups on that.
Yeah.
Yeah,
Yep.
pretty cool work. So you could
Yeah.
probably do some of that with your undergrads.
Yeah, that's part of my hope, hopefully. So
Yes. All right.
yeah.
Do we have any more questions? All right. Well, thank you for your talk today. Really appreciated it and found that I could learn a lot from it. So yeah, thank you for coming.
Yeah. Thank you for the invitation. I hope you guys have a good rest of your day.
You too.
Okay.
Our day is shutting down. Yes, it's probably like, I don't know, 2 o'clock now, 2:30?
Yeah, it's 2 o'clock.
Yeah, we're going for dinner.
Okay, well, have a good evening.
Okay,
Okay.
take care.
Bye.
All right, bye-bye. Thanks, man.